Exercise 1, we can see that what we're dealing with here is I'm an assembly line worker trying to install a particular part, and they either manage to install it or not on each attempt, and the probability of succeeding on each attempt is 0.78. So you can see that we have trials here. Each attempt that the worker makes to install the part is a trial. So if we go to part A, in part A here, what we're asked is that on a particular day the worker needs to install 5 parts, and we want to know the probability it will take them 8 attempts. So the thing that we're trying to find the probability of is the number of attempts. So that is our variable, and so the number of attempts could vary. What's fixed is the 5 parts that they need to install. So we have a fixed number of successes, and then the number of attempts is the variable. So this is then a negative binomial distribution that's needed to find the probability. And here's what we're looking at. We need the probability that the random variable takes the value 8, which is given by the negative binomial evaluated at 8, with a parameter of 5 successes needed, and the probability of success is 0.78. Moving to the next one down here, we have we still have the same scenario in terms of the worker and the parts being installed and the probability of a success, but this time they need to install 7 parts, and we want to know the probability it will take them between 10 and 15 attempts. So again, it's negative binomial. The difference here is that we're looking for a range of values, and here is the expression. You can see the first piece there is our probability statement, followed by a summation that would give us the desired probability, and the same probability expressed in terms of the cumulative distribution. Moving on, here we have a situation where a manufacturer claims that 1 part in 50 will fail under a pressure of 500 pounds per square inch. We're going to test the claim by randomly selecting 5 parts from a batch of 300 and testing them for failure. A part will not be replaced in the batch after testing. So what we can see is that since we're not replacing parts, we're selecting without replacement, and so what we have in this case then is a hypergeometric situation because we're not replacing the parts. We've got a probability of success. We'll actually call a failure a success, and the probability is 1 in 50, which would be 2%. So in this case, in the batch of 300, 1 in 50 corresponds to 6 out of 300. So we would expect 6 bad ones, or ones that would fail in there. And so the question is, if we select 5, what would happen? Okay, so if we go down here, we're asking when we select our 5, what's the probability that exactly one of those 5 parts will fail under this situation? Again, it's hypergeometric, and so we can see here the probability we're looking for is the probability of 1 failure. We can see we have the hypergeometric distribution. The parameters there, the 5 is the number of parts we're selecting. The 6 is the number of failures in the entire population, and the population is 300. So the capital N in our formula is the population of 300, and then the value, the little 6, or the 6 is the little k, which is the number of, quote, successes, or in this case bad parts, in the whole population. Again, same kind of thing as with the last exercise. Now we're asking for the probability that at least one of the 5 parts will fail. What we should observe is that at least one of the 5 failing is the complementary event of none of the 5 failing. And so we can see our probability, the most efficient way to get it is to take 1 minus the probability of getting 0 successes, or in this case parts failing. going to the other side. Here now we have a deck of cards. It has 10 each of diamonds, of hearts, diamonds, and clubs, and 9 extra spades to make up for the missing cards. So we still have a deck of 52 cards in all. We're missing 9 cards out of the hearts, diamonds, and clubs, and we make that up by adding extra spades in. So in this case now, if we go to part A, we can see that we're selecting 10 cards at random with replacement, and we want to know the probability that exactly 5 of them are spades. Since we're replacing and we assume the cards are shuffled in between, then we have a Bernoulli process. The probability of getting a spade remains the same each time, and the successive draws are independent of each other. So in this case we have a binomial situation, and we want the probability of exactly 5 spades in the 10 cards we draw. So you can see here we have a binomial distribution. We're drawing 10 cards and we're looking for 5 successes or spades. There's our probability of a spade, 11 out of 22. That's 22 out of 52 reduced to 11 out of 26. And you can see over here is the result. In the next part of that exercise, we're selecting 100 cards at random with replacement again, and so we want the probability between 30 and 60 of them are spades, including 30 and 60. And so in this case, we're just looking for a range of values again, and here is the probability statement. There's our probability in terms of the PDF, in terms of the CDF, and there's the probability. Now in this case, in part C here, we're going to draw cards until the third spade is obtained, and we want to know the probability that 7 cards must be drawn to obtain the third spade. So now the probability we're looking for is that we draw 7 cards to get 3 spades. So the variable now is the number of cards drawn or trials needed to get 3 successes. So this now has become a negative binomial situation, and our fixed value is 3 spades we're looking for, and we're looking for the probability now that it takes us 7 draws to get the third spade. So you can see here's our probability statement. We're looking for only a single value, 7. Negative binomial, 7 is our variable, the value of our variable. 3 is the parameter, the fixed number of successes we need. And again, there's our probability, and then you can see the computation of the probability. Moving on here, we have a device that's being made containing spacers of thickness between 0.05 and 0.07 inches. Our past experience tells us that the thickness of the spacers that we get from our supplier are normally distributed with a mean of 0.0608 inches and a standard deviation of 0.0047. So when we see normally distributed, that just tells us we'll be using the normal distribution, and we want to know the probability that a randomly selected spacer meets the requirements of being between 0.05 and 0.07 inches in thickness. So we're looking for a range of values. We can see that reflected in our probability statement. We want our random variable to be between 0.05 and 0.07. Since we're dealing with a continuous distribution, we get the probability we want by integrating the PDF, the probability density function in this case. Notice we're integrating with respect to x. We need that dx in there. And but we can get the result without actually doing the integral if we have access to the CDF, the capital N. So we take capital N of 0.07 minus capital N of 0.05. Notice this is the notation used in the book, and it's a standard notation that we'll be using. Of course, in your calculator, you'll enter the 0.05, the 0.07, and then your mean and standard deviation to compute this. But this is the notation I'd like you to use when writing out what we're doing. and there's the value that we get, 0.9641. And here in this portion of the exercise, what you were asked to do is to take the probability we were asked for up here, so the 0.05 to 0.07, and convert that over into the terms of the standard normal distribution. That's the distribution with mean 0 and standard deviation 1. To do that, we use the formula z equals the quantity x minus mu over the standard deviation, mu being the mean, and divide by the standard deviation to convert these values 0.05 and 0.07 over into z values. So here's where I don't show the calculation, but if we take 0.05 and subtract the mean, 0.0608, divide by the standard deviation, 0.0047, we get negative 2.30. Do the same with 0.07 and we get 1.96. So, and that random variable that we've converted to is called z rather than x. So we're looking for the probability that z lies between negative 2.30 and 1.96. Or in other words, we're looking for capital N of 1.96 minus capital N of negative 2.30, where we're using the distribution with mean 0 and standard deviation 1. And you then go and look those up. Sorry, I didn't have my tables handy. We looked those up on these distribution tables. So for the 1.96, we want to be on this side where we have positive values. We come down here to 1.9 in the left column. You would read across on the top column until you get to where there's a 0.06, and those two values come together right there at 0.9750. If I move that down a little, I'm not sure whether we can see. I'm going below the 0.6 and across from, what was it, 1.9. So I need to move the table up a little. So again, that value is right there, 0.9750. For the negative value, the negative 2.30, we need to have the part of the table with the negatives on it. And we come over here, negative 2.30 is the value right there, 0.0107, which we can see here. And so those are the two values then that we subtract and come up with our probability right there, 0.9643. And that concludes assignment 10.